It's time to start I²CNER seminar. So today we have a special guest from Heidelberg University and ISEMS, WPI ISEMS, so kind of the sister, WPI sister, and Kyoto University, Professor Motomu Tanaka. And I'd like to introduce briefly about his CV. And he has been Professor Tanaka graduated from Kyoto University, right? Just I remember. And he has been he got a PhD from University of Munich. Is that correct?
No. I got a PhD in Kyoto.
Kyoto. And then moved to Germany. And now he's a professor of the Heidelberg University and also I don't need to mention in detail. So today I asked him to give a talk, not for energy related topic, but for his specialty area. So title Professor Tanaka's talk is Unraveling Hierarchical Structures, Function and Dynamics of very complex interfaces. So let's welcome Professor Tanaka.
Thank you for the great introduction. So before starting my talk, let me thank Atsushi for his great hospitality to have me here. And it's my pleasure to visit this institute again. Actually, I visited here in March 2013, shortly after the completion of the first construction. And I remember that the labs are pretty much empty at that time. But now I see a lot of activities, and great to see you. I also like to thank all of you for coming and sharing your time with me for this afternoon. So today, I would like to talk about our recent activities on unraveling hierarchical structures, functions, and dynamics of varied complex interfaces underwater. So as Atsushi already introduced shortly to you, so I have been in Germany already for more than 18 years, almost 20 years. So right after my PhD, I moved to Munich, spending 7 years as a postdoc and an independent group leader in the Department of Physics of the Technical University of Munich, where Mössbauer was still active. Then in 2005, I completed another academic degree called habilitation. That's necessary for holding a chair in German universities. In the same year, I got the full professorship at the University of Heidelberg in chemistry and later on in physics. Then since 2013, I'm leading another lab in Kyoto on the basis of dual appointment. So actually, that's my lab in Kyoto and the lab in Heidelberg. You see already that the labs are pretty much international, and also I attracted people coming from the field of physics, chemistry, and medicine, so that they are working together to tackle their scientific challenges. And fortunately, my activities were acknowledged by the Humboldt Foundation and German government. So in 2014, I got a prestigious Siebold Prize from the German President Joachim Gauck at that time at his palace. So this gave me also another reason to contribute to the academic exchange between Germany and Japan. So let me start science. So my fundamental motivation is to understand how nature designs hierarchical structures and functions in general. So as you see, life, in the open and non-equilibrium system, fluctuation of molecules does not result in the heat dissipation exactly like the second law of thermodynamics predicts. In contrast, the break of symmetry generates hierarchical structural orders and function that ranges several orders of magnitude in both lengths, from nanometer scale to the length scales of our body, and time, which is corresponding to the time windows for the dislocation of the defect to the giant membrane fluctuations. So here the key point that we have to note is that nature confines many key reactions at interfaces and utilize them as a two-dimensional reaction space. So when we talk about biological interfaces, so the most prominent example of biological interfaces is nothing but cell membrane that surrounds our cells, in our body. They have already a layer-by-layer structures containing sugar layers outside, lipid membrane with proteins as a core, and the scaffolding proteins underneath. But if we look at cells or cell membranes as materials, their functions can be seen like a super selective filters or super sensitive sensors, but also as a two-dimensional reaction space, as I mentioned. So what we must really think about before going too much to the detail is how does nature confine, or why does nature confine many key reactions in such two-dimensional space? And here I gave a very simple answer, maybe oversimplified. It's an economy of dimensionalities. So we start from the classical Smoluchowski equations of condensation, then calculate the average diffusion time for a particle with a radius r over a distance b to another particle. This is mimicking the characteristic diffusion time to have the chemical reaction to happen. In 2D space and 3D space, one can calculate the dependence of the reciprocal of the, say, probability function of the reactions over time in such a form. And immediately you will see that in 2D space, the probability for particle collision, which is necessary for chemical reactions, does not depend significantly on the particle size. It's in contrast to the 3D situation, where tau scales with 1 over r. This is economically very efficient if you want to run the reaction with molecules with a high molecular weight, such as proteins and protein complexes. So that's the scientific reasons why nature likes interfaces. So if we look at the history of how interfaces have been studied, in the field of theoretical physics, actually, Japan has been a major player leading this field, such as the linear response theory of Ryogo Kubo and Tomita, and also non-equilibrium interface dynamics, which was developed by Kyoji Kawasaki, who was an emeritus professor in Kyushu University, and Takao Oda, who was also an associate with him. On the other hand, whenever we talk with theorists about interfaces, their interfaces, or the theoretical definition of interfaces, is merely a boundary between two bulk phases. This means that the interface has no structure, no function. They are just done. But we know more and more that interfaces have both structures and dynamic functions. The prominent example is a cell membrane. So however, despite of a major development of instruments for surface and interface characterizations, most studies are merely dealing with the structural characterizations under thermodynamic equilibrium. Therefore, a paradigm shift that connects structure, functions, and dynamics of the interfaces is necessary to see interface at work. And that's the reason why I entitled my talk with three key features. So, looking at biological interfaces or cell-cell or cell-tissue contacts, the question is, how does nature physically modulate cell-cell and cell-tissue contacts, which are involving a lot of molecular components? But what's the physics behind? What I show here is an electron micrograph of two neighboring plant cells whose contact is mediated by 200 nanometer thick cellulose layers. Actually, when you look at nature, many cell-cell or cell tissue contacts keep a finite spacing to avoid non-specific tissue adhesion with an aid of biopolymers containing a lot of sugars. So from the generic viewpoint or physical viewpoint, the cell-cell contact can be considered like a problem of wetting. From the viewpoint of thermodynamics, if you think about the situation to have biopolymers with and without biomembranes, which is nothing but the half model of such interface, the additional layer, the presence of additional layer must result in the gain of the surface free energy, which is called as the situation of complete wetting, which can be characterized by the positive spreading coefficient, which is nothing but the difference in the surface tension or free energy between the outermost interfaces, which is the solid-liquid interface in this case, subtracted by the solid polymer membrane-liquid interfaces. Only in case this value goes to positive, you have a thermodynamic, say, favors or energetic favor to sustain such systems stably. On the other hand, if you look at the vertical force interactions perpendicular to the plane of membranes, the interfacial forces, to keep a finite intercellular distance of tens to hundreds of nanometers, the interaction potential at the interfaces should be kept weakly repulsive. So if you look at the force interactions at such complex interfaces, there are many players like electrostatic interactions, van der Waals, hydration repulsions, and entropic forces generated by biopolymers and membranes. It's experimentally almost impossible to discriminate individual players from the viewpoint of experimental physics. Therefore, the common way to do it is to grab the net force acting per unit area called disjoining pressure, which is nothing but the concept introduced by Delyagin, Russian physicist Delyagin, in 60s. So again, from the viewpoint of thermodynamics, disjoining pressure, given as a function of distance between two membranes or two cells, is nothing but the minus or negative sign given to the first derivative of the work you have to invest to change the distance between two planes over distance. This means that the minimum corresponding to the force balance situation can be found only when these second derivatives goes to positive. In contrast, the negative disjoining pressure causes the continuous thinning of the interlayer, which causes eventually the collapse or dissipation, which you can see also when you just feed the poly electrolyte on the oppositely charged surfaces. You have the strong dissipation of the charged polymers. This is called as duality. Therefore, the design of defined cell membrane models with less complexity can reveal how biopolymers modulate or soft materials modulate interfacial interactions. To model biological interfaces with less number of players and with defined molecular components, the strategy that I have developed and established in the past 20 years, more or less, is so-called polymer-supported membrane concept. This is based on the idea of make a half model of cell-cell contacts mediated by biopolymers by the deposition of polymer cushions or polymer tetras supporting the cell membrane models. So the key concept was explained comprehensively in my review published about 12 years ago in Nature. But essentially, what I demonstrated in the past studies is that the ultra-thin polymer interlayers, which has a thickness of tens of nanometers, enable the maintenance of lateral diffusivity and functions of various transmembrane proteins such as ion channels and cell adhesion molecules without losing their native functions. So along this line, we also made a breakthrough in this field, where we succeeded in the control of density and orientation of proteins by spreading native cell membranes directly onto substrates. This is coming from my laziness, or my students' laziness, because they were tired of purifying proteins, reconstitute them into membranes, and deposit them on the substrate. Technicians also hated it. So lazy Motomu just suggested to my student that, well, why don't we just take our cells, throw them onto the substrate, hoping that they are spread on the surface by tuning the interfacial interactions. Many people laughed, including my former boss, Eric Sackmann, who was a pioneer in biophysics in Germany. But we started the project. So actually what we started is to take my blood from the finger, throw them onto the substrate without polymer coating. On bare silica or glass substrate, nothing happens because the adult animal cells are covered with negatively charged sugars, which will be repelled from the glass surface. No adhesion, no rupture. But when we did the same game on 10 nanometer thick polymer supports, after half an hour, we wait, wash away the supernatant, and apply the antibody, which goes specific to the inside of the cells. We got such a picture. You can believe me that this is not the paint made in Photoshop. That's an immunofluorescence picture of my own blood cell membranes stained from inside. It's perfectly homogeneous and continuous film, where you can hardly see any defects or boundary. At least I cannot see. What's nice is when we apply the antibody, which goes to the outside of the cells, we saw nothing. So what's going on? This is nothing but a complete wetting of cell membranes. This means that the cell adheres onto polymer supports, pulled by tension induced by adhesion. Rupture pops up at the weakest link, presumably top or at the bottom, explode the inside, and spread over macroscopically large substrates to create a continuous film. This is nothing but a complete wetting situation, which I explained in one of the introductory slides. So this enables us to get the weapon to transform three-dimensional viscoelastic cells into almost two-dimensional films with perfectly defined membrane orientations. And this is actually the first example of two-dimensional cell membranes. In the following accounts, I demonstrated that the same principle works for other native membranes, such as microsomes, sarcoplasmic reticulum, as well as other plasma membrane extracts. So actually, after the first paper published in 2002, quite some followers appeared, but they never beat us. So we are still the only one team in the world that can fabricate both macroscopic, ranging up to some tens of square centimeters, like a cigar box, as well as a micro-patterned cell membranes, which can be like 10 micrometer wide. So what's good for? So such two-dimensional cell membranes are ideally suited to probe the fine structure perpendicular to the interface by the use of reflectivity-based technique, where we use specular X-ray and neutron reflectivity techniques. What I show here is one of our first X-ray reflectivity results of human red blood cell membrane deposited on polymer support, measured at ESRF, so that's a European synchrotron radiation facilities in Grenoble. So the small trick we introduce here is the use of high energy X-ray. Because the normal X-ray tube or X-ray from the house instrument is all absorbed by water. So in order to guarantee a high transmittance through bulk water, we used this time 22 keV. Recently, I even used 30 kilo-electron-volt, in order to prove the interfaces buried underneath the water. As you can see here in the scattering density plot, the best fit model indicates the deposition of a uniform layer with a clear electron density contrast. And in parallel, we performed the specular neutron reflectivity experiments at Institut La Lavande, again in the same campus in Grenoble, in order to highlight and mask the certain layer of interest or uninterest by contrast variation simply by mixing light water and heavy water. So this enables us to nail down the physical roles of biopolymers in fine adjustment of the interfacial interactions. So again, as I explained to you, the decision pressure should be zero under equilibrium in order to achieve an, say, finite distance between two neighboring cells. So here we introduce very simple asymmetric 5-slab models in van der Waals interaction calculations, and hydration repulsion was plugged in because that decays exponentially over distance. And at the end, we introduced a membrane fluctuation force, which was driven by the thermal activation of the membrane fluctuation described by Wolfgang Herfrich in the 70s. So I would like to emphasize here, without going too much to the minute details, that all parameters calculated to these three measured forces can be measured or were measured or calculated quantitatively. So this kind of full calculation of the interfacial forces enables us to compare the theoretically predicted equilibrium distance and the value measured by diffractivity methods for thin polymers, red, and thick polymers, blue. So for thin polymers, the point of zero force, where the discerning pressure goes across zero, is well defined, where we get the value of value corresponding pretty much well to the experimental results. In case the polymer layer gets 2.5 times thicker, the point of zero force is more vaguely defined, but still we have pretty much good agreement between theoretical prediction and the experimental values. This confirms that the interplays of interfacial forces answering to the frequently asked questions, Motomu, why cellulose does a good job and other polymers don't? Essentially, this is nothing but the balance, counterbalance between a very strong potential minimum created by van der Waals and the strong repulsion generated by hydration. These two are dominant players that confine the position of membrane. So by now, I've been telling you about the situation of polymer-supported single-cell membrane models. But to understand more vividly the role of membrane-bound sugars, which is nothing but this mimic of cell glycocalyx, which is the outer coat of the cell membranes, I designed a model system based on the planar stacks of synthetic and natural glycolipids deposited on planar substrates. I call it as multiple polymer-supported membranes because we are no longer single bilayers, but there are multiple bilayers whose contact is mediated by sugars. To look at the influence of membrane-bound sugars on the membrane mechanics, we introduced an experimental technique called specular and off-specular neutron scattering. It's shown schematically like this, where the incident beam from the neutron source impinges to the planar substrate, planar stacks of membranes, and the scattered beams are detected by two-dimensional detectors like this. Compared to the commonly used powder diffraction techniques, the advantage of using planar geometry is that we can discriminate the momentum transfers or scattering vector components parallel and perpendicular to the plane of membranes, simply from the geometric conservations. Here, the specular intensity reflects the vertical structure information and the information about the interfacial potential or intermembrane potential confinement, while the off-specular intensity gives us information on the lateral structural orderings and the membrane mechanics. So here comes a bit of equations. So to compute the 2D scattering signals detected by two-dimensional detectors, we have to do a bit of math. First, the free energy of the membrane was parameterized or described by revisiting the basic framework in liquid crystalline physics called discrete symmetric Hamiltonian, which was written by Leibler and Lipowski in the 80s. The free energy is described by two principal parameters. One is the compression modulus, which describes the vertical compression modulus of the membrane perpendicular to the membrane plane. The other one is bending rigidity, which reflects the toughness of the membrane against the bending stress. This can be used for any liquid crystalline-like materials with a layered structure. On the other hand, in general, the scattering functions from layered, stratified, rough interfaces within first-born approximations is written as a function of QZ, so Q perpendicular and Q parallel, which I showed you in the previous slides. This is massive, but essentially the important function to note is the function G. This is a displacement correlation function. And basically this guy determines the whole signal. And this function, again it's heavy, is defined by two key parameters. Lambda, called the jump parameter, and eta, called Caillier parameter, two famous French physicists. What's important is both lambda and eta are given by kappa and b. This means that if you compute the scattering functions and gain the best match combination of lambda and eta, you automatically gain kappa and b. So here I show you the comparison of experiment, left, and our model. So here I would like to emphasize that if we integrate these displacement correlation functions from minus infinite to plus infinite, the function disperses. Namely, if you separate 2 points at an infinitely large distance, the roughness goes to infinite, which is nonsense, because we have a planar membranes which are stuck on the surface. So what we did here is pretty simple. We set the finite size of the sample R, which we can measure simply by optical microscopy, which is typically in the order of 1 micron. That's a sample size. By plugging in the sample size, we can make a full calculation of the scattering functions. Here, I would like to emphasize that this calculation contains no single floating parameters. This is the full calculation of 2D scattering functions, which cannot be beaten by, or which has not been beaten by other groups. This enables actually to highlight the influence of, for instance, sugar chemistry on membrane mechanics. For instance, when we take a synthetic glycolipids, we can look at the influence of the conformation of sugar, either bent or cylindrical, reflected to the change in the bending rigidity by factor of 4. Or if we look at the very weak, say, sugar-sugar interactions, which are playing very important roles in the embryonic development, we can see that the sugar density, lateral density of sugar is dominating or is strongly influencing than the vertical compression modulus B. Furthermore, when we go to the natural glycolipids, we can look at the impact of genetic modifications on mechanics. Here we took bacterial glycolipids called lipopolysaccharides from mutant bacteria. Here by genetic mutations, you can cut sugars at any point you want. So this is the kind of model how genetic mutation or evolution influences the membrane mechanics. And this actually highlighted a strong impact of the length of sugars as well as the density of sugars on the membrane mechanics, which was pretty much surprised by the neutron scattering community because nobody ever thought about measuring such complex molecules in a beam of neutron. Actually, in one of these papers, I got a very strange comment from the referee of Physical Review E. He suggested rejection, saying that, well, there are only 3 or 4 groups in the world that can use such kind of measurement on such an accuracy. What's good for the general readership? Don't you think that it's stupid? I found it stupid. So I called the editor, told him that I think it's a flaw to me. Yeah? No, it's my proud to be said that, well, there are only a couple of people who can do it. Wrong, because we are so unique. And that's exactly what we achieved. So here I would like to close this part saying that off-specular neutron scattering unravels the influence of molecular chemistry and genetic and epigenetic mutations, such as diseases, on the mechanics of membrane. So this brings me to another challenge that we tackled, where we shed light on the electrostatics of soft interfaces. This is a subject that I enjoyed when I was a part of the Canadian Center of Excellence, being a Japanese professor in Germany. It's a bit strange, but I got the funding from Canadians, and there I learned from a very prominent microbiologist, Terry Beveridge from Guelph, that the presence of doublet cations, such as magnesium and calcium, increase the survival rate of bacteria against killer peptides by a factor of more than 5. Another one, old theorist David Penck showed me his coarse-grained Monte Carlo simulation, telling me that Motomu's sugar chains containing a lot of sugars with charges should collapse in the presence of calcium ions. I asked him, did you see it? Of course not, because he's a theorist. So I started the experiment, but as all of you can imagine, looking at the textbook, X-ray and neutron scattering yields only the profile of scattering length density or electron density profile in the case of X-ray, but not those of elements. This means that you cannot discriminate sodium and calcium. So to localize element-specific profiles, we introduce another technique called grazing instance X-ray fluorescence. Here, we prepare the model of bacterial surface or sugar lipids, illuminate the sample with a monochromatic synchrotron beam at the instance angle below and beyond the critical angle of total reflection. By changing the angle of incidence, basically you change or you control the penetration depth of an evanescent field. This means that you modulate the illumination volume in the films. Usually, we place a linear detector for X-ray effectivity or a 2D detector for grazing instance small angle scattering, JISAX. But here, we place a fluorescent detector on the top of it. This enables us to gain an element-specific X-ray fluorescence from, for instance, potassium K alpha, calcium K alpha, and so on and so forth, as a function of instance angle. Here, the detected fluorescence intensity as a function of angle of incidence is given as a product of the field intensity, which is an illumination profile, ion concentration profiles, and the element-specific attenuation length. And the elimination profile can be calculated within the framework of the classical abilities formalism for thin stratified films. I skipped the details, but essentially what I want to say is by parameterizing the density profiles of ions as asymmetric Gaussian functions, one can localize the position and the density of ions with a high accuracy. Another point to note is Gray incidence X-fluorescence must be coupled with an X-ray reflectivity because, as you can imagine, the illumination profile, which is nothing but the electromagnetic field traveling in and out of the stratified interlayers, is strongly dependent on the electron density in the thin film system. So without knowing the electron density of each slabs, you have no chance to calculate. Luckily, I had a very good student, two good students, so that in our first paper published in PNS in 2010, we made a very sharp conclusion that the 6 or 5.9 potassium ions complexes with one lipopolysaccharide molecules at the density or at the position of 15 plus minus 3 angstroms. But if we add calcium to the medium, the potassium is completely chipped out, depleted, and 3.5 plus minus 0.3 calcium ions complexes with this molecule at the depths of 16 plus minus 3 angstroms. That's a world record of the ion localization still. So the extremely high spatial accuracy here achieved like plus minus 3 angstroms is not beatable by other spectroscopic methods using normal light. It's only possible by using light with an extremely low or small short wavelengths. So ion or element specific density profile analysis made by GIXF enables the experimental determination of electrostatics of soft and charged interfaces, such as ion bridges that cannot be handled by the classical DLBO theory or Poisson-Boltzmann formalisms because the ion bridges or cross-linking of charged moieties by multivalent ions cannot be handled by the classical Poisson-Boltzmann. This opened the door to look at the ion specificity in Zwitter ionic polymer brushes under the collaboration with the group of I²CNER, and Yuji was coming to my lab 1.5 years ago, yeah, and performed the experiments, which resulted in 1 publication. Actually, such element-specific localization of matter near the interface has a very strong relevance to medicine. Here I took the example of a study on sepsis. In Japanese, it's called I²CNER. So sepsis is a whole body inflammatory response caused by lipopolysaccharides, these bacterial glycolipids released from the bacteria that evoke strong immunological reactions. This is a phase contrast image of an erythrocyte taken from a sepsis patient who is a 6-year-old boy who uptook the soil when he was going for the school excursion and went to the hospital. And I had a friend who is leading the neonatology department in the University Hospital in Heidelberg. And when this patient was about to die, his parents actually asked him to send these blood samples to anyone who can ever help understand the way to fight against sepsis. So this blood sample came to my lab 2 days before the Christmas. My student and I myself uptook 5 different antibiotics because they are heavily inflamed. Then we characterize the mechanical properties of these ones. So sepsis is known to lead to a significant stiffening of the erythrocyte, resulting in such spiky red blood cells. So after these shocking experiences, I started tackling to the mechanics of erythrocyte determined from the fluctuation spectrum, which we call as flicker spectroscopy. The idea itself was surprisingly written in 1975, from Francois Brochard and Lennon in Paris. But we actually took an advantage of modern technology, such as high-resolution imaging and microfluidics. So I had a PC student from Kyoto University in physics, Hiro Ito, for 3 months in my lab, and have him actually perform the experiments with the blood samples coming from the hospital. What we analyzed here is nothing but the Fourier transform of the mean square amplitude of the fluctuation. So we just follow how the radial distance from the center of mass fluctuates in the polar coordinate. Theoretically, Sam Safran in Weizmann Institute wrote a very, universal theorem to describe the mean square amplitude of a cell, fluctuating cells, with 3 principal properties. One is, again, bending rigidity. Sigma is a tension, and gamma here is the spring constant between cytoskeletons and membrane. Namely, how strongly cytoskeletons from the inside is coupled to the cell membranes. This is approximated like a harmonic potential whose spring constant is given as gamma. This is a comparison between experiment and theory, so that we could diagnose the sepsis for adult and neonatal erythrocytes by the use of smart tools in engineering. So by using GIXF, coming back to the scattering, we could actually unravel the mode of actions for antisepsis drug. This is a collaboration with drug developers. So here we actually observed that antisepsis drug, which was in the clinical trial phase 3 at that time, interacts very strongly with lipopolysaccharides, even compared to the normal antibacterial agents on the market used for food preservations. But they interact without destroying the lipopolysaccharide membranes. But in normal cases, if you want to develop an antibacterial agent, you want to kill bacteria, like a sanitary agent in your bathroom. When you see slimy stuff in your bathroom, you want to kill them. Yeah? But these guys bind to the bacterial surface, but they don't kill. They neutralize the bacteria. It was a bit counterintuitive, but it makes actually a lot of sense, because if the drug kills bacteria and destroys the membrane, what happens is a release of toxic lipopolysaccharides in the blood. So the patients are even more suffering from the products given by killed bacteria. So actually, this was the first use of GIXF to understand the mode of actions for drug molecules. Furthermore, we demonstrated in the following papers that the element-specific GIXF can also be used for the localization of not only ions, but also proteins. For instance, when we look at the sulfur K-alpha peak from cysteine involved in the proteins, we can actually calculate the density of cell adhesion molecules attached to the interface. So I propose here that the possibility of this technique for the detection of change in the protein conformation by activation, which is very important for the understanding of the molecular mechanisms of cell adhesion. The next challenge that I want to introduce you, spending another 2 slides, is the challenge towards unraveling level correlation of non-crystalline membrane proteins. Here I found a very interesting subject, also by collaboration with medical scientists. Mark Svenksler, who is now director of the Biocenter in Würzburg. He was introducing me a very nice worm, Trypanosoma, This is a parasite causing a sleeping disease in Africa. This guy is dangerous if you put them in your bloodstream. But no, these guys are very cute because their surface is covered fully with such proteins. Here they have lipid anchors so that they are anchored onto the outer membrane surface. The protein called BSG is achieving almost a full coverage of the animal surface. But in contrast to the S-layer proteins that cover the surface of bacteria, they are never forming crystals. Actually, the dynamic sorting, hydrodynamic sorting of these proteins are the key, scenario for them to survive against a pathogenic attack. Therefore, we actually first started the quantification of the diffusion of membrane-anchored protein in crowded states, which we published last year, and using X-ray, we went to the lateral correlations. So to determine the protein correlation on membrane surfaces, we made use of grazing instance small angle X-ray scattering. When we started this business, there was only one competitor in the world who succeeded in grazing instance scattering of proteins at the interface. This was a group led by Tom Russell in University of Massachusetts. He's a giant guy, or a very heavyweight guy in scattering business. But on the other hand, what he did was still not that fine, I have to say. He actually took tobacco mosaic virus and threw them to the bunch of them to the oil-water interface and shoot it by X-ray. So here, it's no longer a 2D system, although they are confined at the interface. So I decided to go to the model of trypanosoma by anchoring non-crystalline but membrane-bound protein monolayer floating at the water interface. Again here, I combined in the same beamline at the same time the X-ray reflectivity to determine the electron density profile, GRXF for the protein localizations, and in addition to this, we put another detector to detect the surface scattering to look at the lateral correlation. So this can be done only by one beamline in the world in Grenoble for the 3 simultaneous measurements in one sample, which I developed together with the beamline scientist there. So this is indeed the first beautiful GISAX of membrane-anchored proteins we got after some tens of days of struggling beam times. Here we analyze the data with the quantitative calculation of form and structure factor. Here the form factor is approximated like a cylinder, within the framework of distorted wave bone approximation, which is nothing but the approximation considering the multiple diffractions or scattering at the surface. The structure factor, which corresponds to the correlation of the function, structure factor, which reflects the correlation of protein particles, is calculated according to the radial distribution function type formalisms. So actually, we got from the structure factor analysis not only the height and the diameter of proteins, but also we got the correlation lengths, namely the length scales in which the protein can feel each other, precisely as like 20 nanometers, which is about 3 times larger than the protein-protein distance. Again, these are non-crystalline systems, floating at the free floating interface, but we can really quantify how far the organic nanoparticle can feel the others. So actually the use of this technique would be to look at how protein correlation is strengthened or disrupted by the chemical change in the proteins like glycosylation and phosphorylations, but as well as by external factors like the ligand given from the outside. So I introduced the final example of our studies toward the future. So in the title, I talked about structure, functions, and dynamics of the interface. So I told you about structures and functions to some extent. But now I come to the dynamics. Here I want to introduce our recent challenges towards the dynamic regulation of stem cell fate, which was performed under tight collaboration with a group of Anthony Hall. He is a medical director of the Department of Internal Medicine for Hematology and Oncology, as well as the director of the Stem Cell Transplantation Center in Heidelberg. So already in 2015, we published a paper about in vitro human models of acute myeloid leukemia. In Japanese, 急性骨髄性白血病 by using the patient blood samples, discriminate the bad stem cells from the good stem cells. But along this line of study, the grand challenges raised by Tony is first, how can we keep our stem cell young? Because stem cells are now often used for the regenerative medicine, but in culture dishes or in culture flasks, it's very difficult to keep stem cells as stem cells. After some cycles, they are no longer stem cells. It's called as stem cell aging or stem cell senescence. This is the major problem in stem cell biology or base therapy. The second question is, how can we realize the model of the dynamic stem cell microenvironment? So stem cell microenvironment is often called as stem cell niche in vitro system. And this is a key issue to overcome. So actually in Japan, although I don't see him here, Satoru Kidawaki from this university is one of the forerunners in active controls of stem cells using mechanical patterns and gradients. And I take another strategy, which I'm going to tell you now. So here, I decided to make use of physically cross-linked hydrogels based on stimulus-responsive copolymer micelles, which was synthesized by the group of Stephen Arms in Sheffield, which is based on the tetrablock copolymer micelles based on the MPC blocks, or the phosphocholine-based biocompatible part, and the ion-sensitive part. That's the isopropyl amino methyl metacreate. Yeah? So since this part, the isopropyl amino part can be charged and uncharged at the mild pH modulation between 7.2 and 7.8, so that we can tune the degree of cross-linking between micelles, which results in the change in the elastic modulus, Young's modulus, by a factor of 20. So comparison to the other chemically cross-linked gels, which is now used widely in the field of tissue engineering and biomaterial sciences, our advantage is the dynamic capability to dynamically modulate the micromechanical environment, because we simply have to change the pH of the medium slightly out of 7.4. So it's hidden behind, but no, we published the first proof of principle paper in JACS in 2011 by using a very simple fibroblast, myoblast. So the next step is to regulate dynamically the fate of human mesenchymal stem cells derived from bone marrows. So we are really dealing with human stem cells, in that case, coming from the donor directly. In the first step, we demonstrated the ex situ mechanical adaptation of human mesenchymal stem cells. Here, in addition to a very commonly used shape factors like area of projections, aspect ratio, circularities, we add another physical parameter, which is nothing but the nematic order parameter, S. This is again coming from the physics of liquid crystalline. It's used also for the evaluation of how good is the performance of liquid crystalline displays. Basically, the theta is defined as the angle of rod-like elements, in this case cytoskeletons, with respect to the major axis of cell. Simply you assume cells to be like an ellipse, define the theta equals 0, and take the distribution of theta, and you get an order parameter. So when we compare stem cells seeded, cultured on this gel substrates, on the stiff substrates and soft substrates over 10 days, we saw that these guys showed a clear difference. This actually was considered to be like a sign of differentiations of cells towards myoblast or osteoblast and to the neurons somehow. But actually, we tested more than 30 lineage-specific antibodies showing no positive signals. This was discouraging because we thought that, hey, we differentiated the cells or we guided the cell, stem cell lineage, but the antibody test says no. So the postdoc coming from medical hospital, hospital is always medical. Coming from medicine, actually was getting crazy. So she was accusing me in the seminar that Motomu, your concept is a bullshit. Stem cells never cares, but your cells are all going to the wrong directions. But I was turning around the questions, asking myself, can they still be undifferentiated, although the shape looks completely different? She left the lab, I didn't care, but actually I won the game. Here I showed you, sorry, I forgot to put the illustrating animation format. But here we put the multipotency markers to cells that were cultured for 20 days on stiff substrates and soft substrates. We got the hit of more than 95%. More than 95% of our cells are remaining multipotent or undifferentiated, independent from the substrate stiffness. In fact, when we put them into the induction medium, which contains chemicals to induce the differentiations into bones and the fat, they underwent both osteogenesis and adipogenesis. This was actually striking because the multipotency is sustained over 30 days, independent from the thickness. And as I showed, so the cells can undergo both lineage, fat, and bone in chemical induction medium. And this is in contrast or completely against to the big paper published by Dennis Disher's group in UPenn in Cell 2005. I don't know how many thousands of times people cited this paper, and I don't know how many hundreds of groups followed this concept, telling that the substrate elasticity is enough to direct the stem cell lineage. But our finding is completely showing the opposite trend. This was really a big debate when we published this paper. But actually, everybody got convinced afterwards because our data are very quantitative. Another beauty of this material is that we can actually control the stem cell fate by the stress frequency. So as I said, so this gel can change the stiffness at the point you want. So what we did is to change the frequency of stress, changing from soft to stiff, stiff to soft, every 10 days, 7 days, 5 days, and 2 days. Don't ask me why I didn't change every 2 hours or 4 hours, because stem cells are very naive, easy to be contaminated or die. Yeah? So to exchange medium of 30 dishes every second day was already a nerve-killing process for my PC student. But what I plotted here is a fraction of proliferating cells, or dividing cells, or growing cells. As you can see, on plastic dishes, somewhat 50% of them were dividing after 20 days. And it starts dropping sharply after you overcome 7 days or 5 days. And when you go to the very frequent stress systems, like the change in the stiffness of the substrate every second day, namely 10 times in the 20 days period experiment, we see that the proliferation or division of stem cell is suppressed by about 85%. Or in 10 days, it's below 10%. No? The division of cells appears only by less than 10%. So this was actually the new finding, demonstrating that the frequent mechanical stresses suppress stem cell proliferation, which allows actually for the synchronization of stem cells. What I mean is, in the case of in vitro culturing of stem cells for regenerative medicine, what is tricky and what is very difficult is to synchronize the cells. As you may know, cells have their life cycles, dividing, resting, whatsoever. And when you throw them onto the cell culture dish, of course you have the mixture of everything. Yeah? But if we actually stop the proliferation and the differentiations, both, they are basically sleeping. They are not dead. Yeah? But they are kicked out from the cell cycles. And I show that at a certain point, if we put them a cue, like go to bone, go to fat, go to muscle, they start doing the job altogether. So that was beloved by stem cell therapy people. So Anthony Ho, my medical friend, was extremely happy. And from our viewpoint, I enjoyed it because it's nothing but the discovery of a characteristic stress frequency keeping stem cells young and quiet. It will be nice for human beings as well, but to be young and quiet is somewhat intuitive. Okay? So that's the end of the story. So I'd like to thank my people. Actually, she and a couple of people are key engines of the topic that I was telling today. And also quite some junior faculties were already getting solid positions all over the world. And I have to thank also my external collaborating partners coming from sugar chemistry, organic chemistry, microbiology, clinical medicine to theoretical physics, who are generous enough to support all my ambitions with a great patience. And also we got a lot of samples from patients as well. And I hope it appears. Yeah. So at the end, I would like to show you one paper that I published together with a group of I²CNER, based on the results of UG, together with my PhD student in Heidelberg, and my postdoc in I²CNER. Unfortunately, this didn't appear in Nature or Science, but I'm happy enough to see them in an acknowledged form in Journal of Physical Chemistry, because this paper really represents the spirit of WPI program in Kyoto and Kyushu. That's highly international, cross-disciplinary, because my people are all physicists, and the cutting-edge research. So I'd like to thank also for your attention, and I'm glad to take some comments. Thank you.